Hi, everyone. Welcome to lecture 12 of Deep Unsupervised Learning, Spring 2020. Today, we'll cover representation learning and reinforcement learning. First, before I start, I want to give a big thank you to many colleagues and friends who have contributed to this lecture through sharing their insights, illustrations, slides, and videos that all have very directly contributed to what I'll be sharing in this lecture here today. Thank you. So generally our class has been about unsupervised learning. Today, we're actually going to look at how unsupervised learning and reinforcement learning can be brought together in a way that unsupervised learning can make reinforcement learning more efficient. But we haven't covered reinforcement learning yet in this class. And so what I'm first going to do is step through some of the very basics of reinforcement learning. Obviously can't cover everything. It could be a course in itself, but we'll go through some of the basics, some of the recent successes, and then from there, look at successes where unsupervised learning and reinforcement learning were brought together. So what is reinforcement learning? Reinforcement learning is a problem setting where you have an agent. Agent's supposed to take actions in the world. After the agent takes actions, the world will change. So for example, the world could be the robot body and the environment around the robot body. And after the world has changed because of the agent's action, this process repeats over and over and over. And the goal for the agent is to maximize reward collected in the process. For example, imagine our agent is supposed to control a self-driving car. Then the reward might be positive for reaching destination and negative for getting into an accident. Maybe our agent is a robot chef, and then the reward might be positive for a good meal, even more positive for an excellent meal, and negative for making a total mess in the kitchen. And the goal in reinforcement learning is for this agent to figure out through its own trial and error how to get high reward. So as the human designer who gives the specification, we just say, hey, I'd like high reward, and you say reward is high for the things I just described, and then the agent's supposed to figure out on its own how to achieve that. Another example could be a video game. The score in the video game could be the reward, and so the agent's supposed to figure out how to play that game to maximize reward. What are some challenges in reinforcement learning? And let me contrast it with supervised learning. So in supervised learning, what happens is you have an input and a corresponding output. And the way you supervise your learning system is by saying for this input, that should be the output. For this other input, that should be the output, and so forth. In reinforcement learning, your robot chef might be busy in the kitchen for a half hour, comes out with its meal, and you might say good or bad meal, but that's not reflective of the last action the robot chef took. It's reflective that whole half an hour of work in the kitchen that somehow resulted in a high reward or a low reward. And now when that robot chef cooks multiple times and sometimes has good outcomes, sometimes bad outcomes, you could start looking at what's common between the good outcomes. What's common among the bad outcomes? That process of teasing apart what might have positively contributed, what might have negatively contributed, that's solving the credit assignment problem. It's one of the big challenges for a reinforcement learning agent. Another big challenge is stability. When, let's say you have an agent learning to fly a helicopter. Well, helicopters are naturally unstable, so if you're not careful, during the learning process, you might crash your system, and that might just stop the whole thing. Another big challenge is exploration. For a reinforcement learning agent to learn to do things, if it initially doesn't know how to do anything, it has to try things it's never done before. It has to explore. And this is many, many challenges. When you try things you never tried before, well, how do you even know what you should be trying? There could be so many things to try. What's more interesting? What's less interesting? And it also brings back the stability challenges. How do you make sure when you try something, you don't destroy the system and so forth? Now, one example that many people would know in real life of reinforcement learning is how to train a dog. When you train a dog, the dog is the reinforcement learning agent. And you as a human provide rewards. You might give the dog positive reward when it does well and negative reward when it does poorly. And you don't control what the dog does. It's not supervised. You cannot tell the dog, do this, do that, and it'll just, all its muscles will follow your commands. No, the dog will just do some stuff and he'll say good or bad depending on how happy you are with what the dog did. So one of the things that we want to do in today's lecture is give you a bit of an overview of successes of reinforcement learning, but then also from there look at limitations and take a look at how representation learning can help out. So one of the successes, or probably the success that put deep reinforcement learning on the map, was in 2013 when DeepMind came out with the DQN results. DeepMind showed that it's possible for a neural network to learn to play a wide range of Atari games from its own trial and error. Now, this was a big surprise. Until then, if you looked at reinforcement learning results, they would typically be on relatively small, simple environments, and the input would not be images. The input to the agent would be a very well-crafted representation of whatever world the agent is in, summarizing it in a small set of features or state variables. And so, big surprise, all of a sudden, reinforcement learning works with pixels as input. From there, a lot of progress was made, of course, including the progress listed on this slide here, a lot of it coming out of also DeepMind, Berkeley, OpenAI, and much, much higher scores and faster learning has been achieved on the Atari result, on the Atari benchmark since. It wasn't just Atari. DeepMind also showed it can learn to play the game of Go, long-standing challenge. Many people thought it would be another 20 years if you asked them in 2013, 2014. But sure enough, in 2015, a computer beat the world champion in Go. And then the first version, AlphaGo, was a combination of imitation learning and reinforcement learning. The second version, AlphaGo 0, was pure reinforcement learning. It just learned from playing against itself, and over time became better than the best human players. And then was a big result in more advanced gameplay or video gameplay. OpenAI showed that the game of Dota 2 can be mastered by a reinforcement learning agent. In 2017, it was shown that a reinforcement learning agent can master the one-on-one version of the game and beat some of the best human players. And then a little later, it was shown that reinforcement learning enables playing at very competitive, not necessarily beating the human world champion team just yet, but at a very competitive level with some of the best human teams through pure reinforcement learning. At Berkeley, in parallel, we were exploring reinforcement learning for robotic control. And so here is actually some reinforcement learning in action. Thus far, we just talked about results. What does it look like when you see it in action? Here we see an agent that's learning to control. In this case, is learning to run. And we give it positive reward. The more positive, the more it moves to the right, and it's negative reward for falling onto the ground. And what we see is that over time, it figures out a strategy, a control policy that gets it to run off to the right. Now, the beauty here is that it's able to learn this in a way that is not specific to this two-legged robot, meaning that we can run the exact same deep reinforcement learning code and run it on a four-legged robot. It'll learn to control this four-legged robot. And in fact, it can also learn to play Atari games. The exact same code, in this case, is Trust Region Policy Optimization, TRPO, combined with Generalized Advantage Estimation, GAE, that's able to learn to master all their skills. In this case, the robot's learning to get up. The reward is based on how close the head is to standing head height. The closer the head is to standing head height, the higher the reward. And then this was generalized to a much wider range of skills. So what you see here is a reinforcement learning agent that has mastered a very wide range of locomotion skills. And then here we see it in action on a real robot. This is Brett, the Berkeley robot for the elimination of tedious tasks, because we humans don't want to do the tedious tasks. We want robots to do those tedious tasks for us. And what you see here is this robot is learning to put the block into the matching opening. And indeed, over time, it figures out how to get the block into the matching opening. And what it's doing under the hood, it's learning a vision system and a control system all together to learn to complete this task. What's the catch in all of this? Data inefficiency. Well, mastery is achieved in Atari, in Go, in robot locomotion, robot manipulation, and so forth, this mastery requires an enormous amount of trial and error. And so the big question is, can we somehow bring that down and reduce the amount of trial and error that's required to master these skills? It turns out, I believe, and many others believe, that representation learning can play a big role in getting there, to get to much more efficient reinforcement learning. And it's not something that is fully understood yet. This is a domain with a lot of room for more research. And so what we'll cover today is I would say, pretty wide range of highlights of relatively recent results people have achieved by looking at combining representation learning with reinforcement learning to make RL, reinforcement learning, more efficient. We'll look at this along 4 directions: auxiliary losses, state representation, exploration, and unsupervised skill discovery, and we'll unpack these as we go along. One thing you'll notice is that it's not some kind of linearly building up thing, and at the end, it culminates in what is the most important piece. Really, what we're going to be covering is a wide range of highlights that each has their own interesting factors to it, and probably a solution that will be the final solution in the future will combine ideas from many of the research results that we covered today into one system. So let's start with auxiliary losses. The paper I want to start with is the Unreal paper by DeepMind. So the idea here is that reinforcement learning, as I said, can be very data hungry, especially if there's only sparse rewards. And the question is, can we make an agent learn more efficiently by having auxiliary prediction and control tasks, by having the agent not just learn from reward signal, because it might be very sparse, but have the agent absorb other signals. Of course, not signals we want to supervise as a human, because then it becomes very tedious, but self-supervised signals, signals that are available in the environment that the agent could try to learn from, even if it's not exactly reward signal. So the Unreal agent, which stands for Unsupervised Reinforcement Learning and Auxiliary Learning, showed a 10x improvement in data efficiency over A3C, which can be standard RL approach DeepMind would use at the time on the 3D DeepMind Lab, which is a navigation, first-person vision navigation task, and 60% improvement in the final scores. So faster learning and converging to better final scores. So what does the architecture look like? What we see at the top here in the middle is the base A3C agent. So again, this is not a reinforcement learning lecture, but let me give you a little bit of background on what's going on here. In reinforcement learning, you have experiences. The agent, without any given time, when it has to make a decision, take in the current input, process it, and then through the policy output, try to make a decision on what to do, and through the value function output, try to predict how much reward is going to get in the future from this moment in time onwards. So there's 2 output predictions here, and that's the standard base A3C agent. So it already predicts 2 things: how much reward, that's V value, the cumulative reward over time that's coming, and policy pi, action it should be taken. So both of those are outputs of the same network. That's the base A3C agent. Then all the data gets put into a replay buffer and is reused in other ways, and the same neural net that is the A3C agent will give it multiple heads, even more heads, so it has to make even more predictions. And by giving it additional prediction tasks, if these prediction tasks are related to learning to solve the original problem, which is achieve high reward, if these prediction tasks are related, then hopefully it'll learn something that'll transfer over to the real task we care about and be able to learn the real task more quickly. So what are these auxiliary tasks? The first one is auxiliary Q functions. So the idea here is you give additional heads to the neural network that are Q functions. A Q function is predicting for the current situation, how much reward will I get in the future if I currently take a specific action. So for each possible action, it'll predict how much reward might I get. Now, the interesting thing about Q function learning is that you can do Q function learning off policy, meaning you can try to solve one task, but in the meantime, do Q learning against the other task that has a different reward function. And that's the key idea here. We're going to take reward functions that are not the ones we care about, that are auxiliary reward functions that are easy to automatically extract from the environment, and do Q-learning against those reward functions. And by doing so, the core structure, the core of the neural net will learn things that are also useful for the task we actually care about. Okay, so let's actually dive a little deeper here. So base A3C agent is the core thing. The sparse rewards means you just, here's the cake from Jan LeCun. You get this one cherry on the cake from the real reward that we care about. That's not enough. We want more rewards. And that's exactly what this Q function thing is going to do. We're going to define many other rewards. And these many other rewards are going to allow us to learn from a lot more signal than if we only had our one reward. Okay, so this reward function that was defined here by the authors of the paper is called a pixel control reward function. And so what they do is they turn what the agent sees, first-person vision of the maze, into a coarser, in this case, grayscale kind of representation of what it's seeing. And you get rewarded in this auxiliary reward task for how much you're able to change this coarse pixel value. So what does that mean? If your agent turns into a direction where things are much brighter than the direction they're facing right now, then the pixel values will change a lot, and that would be a high reward thing. Or other way around, if right now things look very bright in a certain pixel and an agent turns and makes that pixel darker, that would be high reward. Again, that's not what we actually care about, but it's a very simple auxiliary loss that we can impose and that we can run Q-learning against. And so it also turns out that this is the one that mattered the most for improving the learning. There are other auxiliary losses, but this is the one that matters the most. In intuition here, why this one matters the most is that in Q-learning, you are learning about the effect of your actions. And so because you're learning about the effect of many possible actions you could take, what would be the Q value if I turn to the left? What would be the Q value if I turn to the right? What would be the Q value if I look up, look down? And this way, you're really learning something about how the world works. And not just how the world works, but how your actions interact with what happens in the world. Another auxiliary loss is reward prediction. So what you do here is for your current policy that you're executing, you can try to predict at future time steps how much real reward you're going to get. So maybe you get reward for eating an apple. And so when you see an apple in the distance, you should be able to predict that if you keep running forward for 3 more steps, you'll get that apple. And so learn to predict that in 3 steps, you're going to get that apple is an auxiliary loss that's introduced here. And then a last auxiliary loss is value function replay. So it's saying from the current time, how much reward am I going to get over the next few steps? And so this ties into what's already in the base A3C agent, actually. All right. So if we look at results here, this is on DeepMind Lab, which is that 3D navigation environment where you collect apples and other fruits as reward. We can look at different approaches. So the bottom curve we're looking at is the base A3C agent. Okay, so that's the dark blue bottom curve. And the hope is by having auxiliary losses, we can do better. If we incorporate all the ideas that we just covered, you get the Unreal agent, you get this top blue curve here. And what we see here is various ablations to see, well, which one of these matters the most and which ones might not contribute very much. What we see is if you just do the Q-learning for pixel control auxiliary loss, that's the yellow curve, you get almost all the juice of these auxiliary losses. But if in addition you have the reward prediction and the value replay, you have yet a little better performance. So actually, another thing I want to highlight here, what's on the top of the graph here says average of the top 3 agents. So there's a way to evaluate things in the paper, usually in reinforcement learning, because you need to explore and there's a lot of randomness in exploration. The results are somewhat unpredictable, meaning that some runs will be more lucky than other runs, and there'll be high variance. And so what they did here, they picked the top 3 runs. You might say, why the top 3? That's a little crazy. Shouldn't you look at the average performance, anything like that? Yeah, you could argue you should look at the average performance. It's what's done in most papers. But the thinking here was that imagine what you're interested in is finding a policy. And you have maybe a budget of doing 20 runs. then maybe what matters is what's the best one among those 20 runs, or to be a little more robust to variance, how did the best 3 runs do? And so an approach where the best 3 runs are consistently great, then that's an approach where if you're willing to afford 20 runs total, you'll have a good one among them. And so it's kind of a funny way to score things, but it happens to be how they did things in this paper. So another thing we compared with, which we as unsupervised learning students, of course, be very curious about, if you do pixel control, why not do feature control? Why not a Q function for kind of later layers in the network? If for later layers in the network, I want to see if I take an action, can I change the feature value in maybe layer 5 or layer 6 instead of just pixel value change? Well, we see A3C plus feature control in green, and A3C plus pixel control in orange. And we see the pixel control actually works better. Of course, this might depend on the environment. This might depend on exact neural net architecture, but the experiments that were done in this paper show that pixel control actually slightly outperformed feature-based control. And again, control here means it's the auxiliary loss used in the auxiliary Q functions. It's the ultimate reward function that you actually optimize for and score against on the vertical axis here is the real reward function of collecting the fruits in the maze. Then here are a couple of unsupervised RL baselines. So what are some other things we're looking at? Again, A3C plus pixel control shown in yellow. That's the top curve in both plots. Then input change predictions. You just try to have an auxiliary loss that says, can I predict how what I see will change as a function of my actions? So that's really learning a dynamics model. That's shown in blue. And then shown in green is input reconstruction. So that's a bit like a VAE. I have an input, make a latent representation, reconstruct it back out. And so what we see is that these things that might seem maybe more natural or more advanced, like input reconstruction or input change prediction, are actually less effective than pixel control. And of course, I mean, there could be many factors at play here, but the high level intuition that most people have is that the reason these auxiliary Q functions work so well is that what's happening here is that as we work with auxiliary Q functions, we're actually learning about not just how the world works, which is the input change prediction, but how we are able to affect what happens in the world. And that's really what matters for learning to achieve high reward on the task you care about. Now, another domain they looked at, rather than first person maze navigation, is Montezuma's Revenge. Montezuma's Revenge is a famous Atari game where exploration is very difficult. There are many rooms. In every room, there's complicated things you have to do, collecting keys, jumping over things. You make one mistake, you're dead, and you start back at the beginning. Shows here that Unreal outperforms A3C by quite a bit. A3C here at the bottom in black is really not getting anywhere, whereas the Unreal approach is actually doing a lot better. Now let's take a look at this maze navigation agent in action. So this is DeepMind Lab. Let's take a look at the agent playing. So agent's collecting the apples here, not collecting the lemons. That's apparently it's not good in this particular game to collect the lemons. And so this agent has learned to navigate mazes. The way it can do that, by the way, is because it has a LSTM, which gives it memory, so it can remember places it's been before and things it's tried before to more efficiently find the next new location where there might be a fruit it hasn't collected yet. And so the reason I'm showing these specific results here is because the space of, well, reinforcement learning in general, but especially representation learning and reinforcement learning, the evaluations aren't all in the same type of environments. There's a lot of variation in how these things get evaluated. And so having a good feel for what these experiments actually look like is important to get a sense for how advanced might this method really be. And so we see here as well, this first person navigation, well, that's pretty complicated. So this might be a pretty advanced method at play here. Here we see a little bit of an inside look into the agent itself. where on the top right, you see the pixel control Q values. It's saying, okay, depending on which action I take, there's 4 actions available. How high will my Q value be, which really corresponds to an understanding of how the world works, what will change in what I see as a function of actions I take. All right, so to summarize, the Unreal loss is the original A3C loss, which is just a policy gradient plus value function loss. Then there is value replay loss, which looks at replay buffer value prediction. And then there's the pixel control Q functions for different coarse pixels in the view of the agent. And then finally, there's the reward prediction loss. Small little thing in the reward prediction, they ensured there was an equal portion of rewarding and non-rewarding examples, so a balanced training set. The pixel control did split into a 20 by 20 grid of cells. All right, so in the Atari results, we see that Unreal also helps over A3C, but not nearly as much as in the DeepMind lab environments, but still a significant improvement. The vertical axis here is human normalized performance. So the way DeepMind is evaluating this is they look at what humans tend to achieve, and that for every game, that's going to be a different score because every game has a very different scoring system. And then they normalize it across games and have a total score across all games, how well the agent learns. So this is across many, many Atari games. It's tens of Atari games. On average, how fast does the learning curve go up? So you can't have like overfitting onto one game or the other and do well on this score. You need to be able to learn well on all of the games to do well on this score. All right, and then also look here at robustness, because there's many agents being trained, and these top 3 curves don't necessarily expose performance of all the agents. Here's a little bit of evaluation of robustness. And we'll see that, there's a bit of decay in performance. Not all agents learn equally well, but it's not that there's just one that does well and then nobody else does well. So this looks pretty good. Okay, so that's the first thing I wanted to cover, which is auxiliary losses, and Unreal is a very good example of that. There's more work happening all the time in this space, but that was kind of the big initial result that showed this is something that can be very beneficial. Let's switch gears to state representation, and under this we'll have many, many subsections, it turns out. First one we have is how we go from observation to state. So the kind of paper that most people might be most familiar with is the World Models paper by David Ha and collaborators. And here's very kind of simple diagram showcasing what they investigated. So what you have is you have an environment. The environment leads to an observation. In this case, pixel values. And that can be very high dimensional. If you have a, let's say, 100 by 100 image, that's 10,000 pixels. That's a very high dimensional input. Then they say, well, that's high dimensional. We want our agent to work on something lower dimensional because we know under the hood, there is a state of the world. And the state of the world might be summarized well in just a small set of numbers, maybe 10, 20, 30 numbers is enough. So my agent shouldn't have to operate, shouldn't do reinforcement on those 10,000 number input, should be doing reinforcement on just a 30 number input, and might be able to learn a lot more quickly because credit assignment should be easier if we only have to look at 30 numbers instead of 10,000 numbers. And so it is that you, in this case, train a variational autoencoder, which we've of course covered in the early weeks of this course, to find a latent representation that from which we can reconstruct the original, but then we'll use the latent representation as the input to the reinforcement learning agent, which now hopefully will be more efficient. So what we'll then do in this approach is train a recurrent neural network that learns to predict the next latent state. So what's going to happen here is we're going to learn a way to simulate how the world works in this recurrent neural network, but not by directly simulating in pixel space, but by simulating in this latent space, which could go a lot faster because a lot lower dimension. We don't have to render the world at all times. We can just simulate how the latent variables evolve over time. Of course, this will also depend on the action state. So it's a model that depends on action and previous latent state generate the next latent state. And of course, you want it to be the case that that matches up with the actual next latent state that your VAE would output when you get to observe the next latent state. And then the action gets fed into the environment also. And this, so you have kind of two paths here. You have the actual environment path, and you have the RNN prediction path, and you hope that they line up. Or you train it, really, to make this line up. The thing in blue is called the world model, is a thing that looks at the latent state Z, turns it into, try looking at action latent state, turns it into next latent state. All right, so they looked at this in the context of car racing. So on the left, you see the environment. It graze the road, so you're supposed to stay on the road here, the way the reward is set up, and race down this road as quickly as possible. This is from pixel input, so you get a lot of numbers as input, and somehow you hope that would get turned into effectively an understanding of roughly where the road is, where your car is on that road, and which direction it's facing your car, and then understand how to steer it to go down the road as quickly as possible. The procedure they followed is they collect 10,000 rollouts from a random policy. Then they train their VAE to encode frames into Z space, just 32-dimensional Z space, so very low dimensional compared to the pixel input space. Then they train a RNN model to predict next latent state from previous latent state action, and there's this additional latent state inside the RNN. Then they use evolution, but it's just one of many possible RL approaches to train a linear controller to maximize expected reward of a rollout. So step 1, 2, and 3 is the unsupervised learning that can happen ahead of time. And then you can run RL on that representation that you've learned. So one thing that's real interesting here is that, remember the Jan LeCun cake, where Jan would say, oh, well, you know, reinforced learning is the cherry on the cake, which is tiny compared to the cake. And why is reinforced learning the cherry? Because there's not a lot of reward signal. It's just a small amount of reward signal. The volume here corresponds to the amount of signal. There's a lot of signal coming from self-supervised learning, and that's the foundation of the cake. And so if we look at what's happening here, the VAE neural network has 4 million parameters. The RNN dynamics model neural network has 400,000 parameters. And then the controller, the thing that is learned with RL, only has 800 something parameters. So there's a massive difference in that RL only has to learn a small number of parameters, which maps to it only have a lesser amount of signal, whereas the self-supervised part has to learn most parameters, millions of parameters, and that's done from unsupervised data. Okay, so here's an example of an input frame. They use 64 by 64 pixels here and a frame reconstruction, which kind of roughly matches up, not perfectly, but it gets the gist. Then here we have, when we use just Z or Z and H, H is the RNN's hidden state, so it shows that's important, that the RNN hidden state captures something important about the world. Let's look at results. So what we see here in the table is scores attained with the model described, highest score in this car racing environment compared to previous methods. Obviously, in principle, other methods should be able to learn this too, but when you limit the amount of time you get to train, then using self-supervised learning to learn a representation combined with reinforcement learning to learn the control allows to get significantly higher scores than previous methods that were pure RL were able to do. So this is the model we looked at before. One experiment we saw so far had the car racing environment. The second experiment to look at is the kind of where you have to dodge things being shot at you in a Visdoom environment. So the input will look something like what you see on the left, but sometimes you'll see fireballs coming at you when they're shooting at you, and you got to dodge those fire bullets to stay alive and get high reward. Same approach, train a VAE, train an RNN world model, then linear controller trained with RL on top of that. And so again, this linear controller trained on top of that is trained in the RNN simulator itself. So you don't need to simulate what things will look like. Rendering is often expensive computationally. If you need to go all the way to rendering to train your policy, it'll take a lot longer to do the same number of rollouts. You're able to stay in that low dimensional latent space to train the policy. So It's called Doom Take Cover. Here's a higher resolution version of what this looks like if you were to play this game yourself. Same approach laid out here. Again, unsupervised learning does all this stuff at the top here. Millions of parameters learned. Then the RL only needs to learn about 1,000 parameters. Again, beautiful instantiation of the Jan LeCun cake idea. So here is what here's what this looks like. One thing to keep in mind here is that it actually sometimes you can have some quirky results where the simulator of the world allows you to do things you cannot do in the real world, and so that's something to look out for that they're highlighting on their website. So if you go look at the kind of normal temperature, higher temperature things, you'll see some differences there. So here are the results. We have, depending on the temperature, different discrepancies. So for low temperature, we see a very high virtual score, but the actual score not so great. For higher temperatures, we have a closer match between the virtual score and the actual score. So actually, I should quickly highlight what we mean with temperature here. So typically in RL, you have a policy that has stochastic output. So you would have a distribution over actions, and the distribution over actions can have a temperature parameter in terms of how much you favor your favorite action. And so that temperature parameter, if you make it small, low, close to 0, then you'll always take your most preferred action. When you have, then you end up with a close to deterministic policy. When you have a close to deterministic policy, you can often exploit quirks in your simulator. Whereas if you have some randomness in your policy, you have a higher temperature, you force yourself a little bit of randomness, then you could not exploit very specific quirks in the learned simulator because the randomness will prevent you from being able to go that very, very quirky path where you all of a sudden get a high score, even though really you can't do that in the real world, but your simulator has a small little bug. You won't be able to trigger that small little bug. And that's what's going on here with temperature. At higher temperature, we are not able to exploit tiny little bugs in the learned simulator. We have to learn something more robust. And that leads to a better match between performance in the real environment relative to the learned simulator. Okay, so that was the world models paper by David High and collaborators. Now, one question you could ask yourself, if we're going to learn a world model, we're going to learn a simulator, some latent space simulator, could it make sense to try to learn a latent space such that control becomes easier? What do I mean with that? So if you look at the control literature, some control problems are easy to solve. Some control problems are very hard to solve. And maybe we can map our pixel observations and world dynamics in pixel space into a latent space dynamics that satisfies certain properties that make the resulting control problem easier to solve. A good example of this is linear dynamical systems. If you have a linear dynamical system, then the control problem tends to be relatively straightforward to solve. So how about this then? And this is what this paper we're going to cover here is going to do is, hold on, give me 1 second here. Actually, let me cover something else here first. So one thing that might happen is as you train a world model on your randomly collected data and then train your policy and test it in the real world, it might not always work. The reason it might not work is because the randomly collected data might not have been interesting enough to maybe cover the parts of the space where you would get high reward. And so what then you'd want to do is iterate this process. At this point, you effectively have a model-based reinforcement learning procedure. You collect data, you learn a model, you find a policy in the learned model, you deploy that policy, you take the new data, improve your world model, and repeat. So that's what they did in this case for the cart pull swing up. And so after about 20 iterations through this, they would be able to learn to swing it up. Now, a couple of other world models papers is the action conditional video prediction using deep networks in Atari games. Listed at the top here, worth checking out. Model-based reinforcement learning for Atari is another one worth checking out. And then learning rate dynamics for planning from pixels, Planet, which we'll look at a little bit later also. So if you want to look more closely at the specific paper we just covered, there's a really nice website, worldmodels.github.io, which has the code, which has many demos for you to play with what actually the latent variables are doing and the VAE and so forth for these environments. So I highly recommend checking that out. And here is a video of the Vizdoom cover in action. So you get these fireballs coming at you, and the agent has learned to get out of the way to not get killed. All right, so we looked at so far is we looked at how to go from observation to state and then learn a model in that latent state space. Now we're going to take a look at going from observation to state, but also from state action to next state. So, and this is what I earlier alluded to, and I jumped the gun a little bit on this, is we're going to now do representation learning that's not ahead of time, learning representation from pixel to hopefully state or something like state, but that is already, when it's doing representation learning, looking at the dynamics. And so when we look at the dynamics during representation learning, why not learn a representation where the dynamics is such that control becomes easier? For example, learn a representation such that in this new representation space, the dynamics is linear. Because if the dynamics is linear, then all of a sudden control becomes easy. And you turn your original pixel space problem, which might be highly nonlinear, very complex to have a control methodology for, into a latent space problem where it's just linear and very simple to solve. And that's the main idea behind this embed to control paper we're covering now. So the systems they considered were pendulum, cart pull, and 3-linked arm. But again, this is from pixel, so it's going to be pixel input, learn a latent representation where hopefully dynamics is close to linear and hence control becomes easy. So it's called stochastic optimal control, the method they applied. It's kind of a standard control method that you could apply to linear systems. And embed to control will learn a latent space model using a variational autoencoder while forcing a locally linear latent space dynamics model. So once you have a locally linear model, you can apply stochastic optimal control as an example of that in action, where once you have such a model, it's very easy to find the controller that brings you to a target, let's say a stable fixed point, thanks to that controller. For this to work well, locally along these trajectories, you need to have linear dynamics models. And in fact, the way these methods work is they tend to linearize the dynamics along trajectories. But what if you learn a latent space model where it's already linear, you're already good to go, and that linearization will not be an approximation, it'll actually be the actual model that you learned, so that it'll be nice, you'll have a very good fit of your linear model to the actual dynamics. So the costs are often assumed to be quadratic. So that's an assumption to make, this class of problems called LQR problems, linear quadratic control problems, sometimes LQG problems if you also have some stochasticity in there. And these problems assume that you have linear dynamics and quadratic cost. Quadratic cost meaning there's a quadratic penalty for being away from the state where you're supposed to be. Okay, so of course, we can't just go from our original pixel observations to some space where dynamics is linear and ignore the real world dynamics. That's to map back out the real world dynamics. So let's look at the complete loss function to look at. First of all, you go to latent space Z. You need to be able to reconstruct the original image. So Z should not lose important information about what is happening here or what's the situation here. Then we have this temporal aspect here. And ultimately, we want to reach a goal and want to have long-term act prediction that in the end, for the sequence of actions that achieves the goal, it also predicts that's going to be the case. So every step along the way, we're going to have predictions and we're going to use linear models. So prediction must be locally linearizable for all valid control magnitudes, such that when we optimize our controls, we get something that, when it works in simulation, also works in real world. And we're going to force that to be true by learning a model that does this by construction. So let's look at that model. Here's the next component. We already have our encoder, decoder. We have our control input U. So in controls, usually U is used for control input, and reinforcement often A is used for action. Controls U for controls. Then we have our next latent state ZT plus 1. And for this to be meaningful, the same decoder should be able to reconstruct the image input at time t plus 1. If that's the case, then that latent space dynamics was correct. Okay? And so we're going to learn a locally linear model here in that transition to make that work. Okay, then once we have all that in place, we're pretty much good to go. We're going to use this model over long horizons so to make sure that we don't just do this over one step, but we actually lay this out over longer horizons. And as we train the model, we have multi-step predictions over which we have this loss function. You might say, why do we need all this? Well, it turns out that if you make a small mistake in your prediction for the next state, then you might say, not bad, just a small mistake, no big deal. But if you make that small mistake, the problem is that you land in a new latent state for which your model might not have been trained. And when you make the next prediction to go to time t plus 2, you're doing it from a time t plus 1 latent state that you're not familiar with, that doesn't lie in your training distribution. And now you might make a not so good prediction, make it even worse. And this is an accumulation of errors over time can lead to divergence. And so we need to explicitly avoid that. Any kind of simulation that needs to run over longer horizon needs a mechanism to avoid that. Okay, so one mechanism is to explicitly have a loss over multi-step. Another mechanism is to ensure that your next state prediction comes from the correct latent distribution. So if you embed into, let's say, unit Gaussian space, then after you do your next state prediction, it should also, that what you get there should come from a unit Gaussian distribution to ensure that when you go from there to the next one, you're ready to make your predictions. All right, so those are the components. We have an autoencoder to turn image X into latent state. We have accurate long-term prediction of latent states because we ensure that the next latent state comes from the correct distribution, a unit Gaussian, just like our autoencoder forces it to be. And then the prediction must be locally linearizable. So we don't get some fancy neural network to predict the next latent state from the current latent state. It has to be feasible with just a linear prediction. Okay, so this is then the full system that they propose, all the loss terms shown at the bottom. And let's take a look at how all this works. So they apply this to CardPol. Nasha showed a good amount of success in CardPol. And here are some evaluations on that, showing that embed to control indeed can do inverted pendulum swing up pretty well. It can do CardPol balance, it can do 3-link arm. So good results on 3 environments that they experimented with. And here's what these environments look like. This is from raw images. So what we're watching is effectively also what the agent sees, though the agent will often see a downsampling. So let's take actually a look at the environments themselves. So real image on the left, reconstruct on the right. And here we have CardPol balancing in action. And so this gives you some idea of how capable this approach is. So it does very well. At the same time, clearly these environments are not nearly as complicated as what we saw in the Unreal environments, where it was DeepMind lab navigation tasks versus these kind of 2D, relatively low resolution, single robot that you fully control kind of tasks. Now, in embed to control, the idea was to have a single linear system for your full dynamics. That might be difficult. What's been shown in controls is that very often, even though your real system is highly nonlinear, locally, it can be linearized. And so you might ask the question, can we instead follow the same philosophy as embed to control, but instead of learning a single linear model, can we learn just a collection of linear models in some way that allows us to apply time-varying linear control methods, which are also extremely efficient, and maybe have a richer set of environments that we can solve for, because time-varying linear models can cover more than just a single linear model can. That's actually what we did in this work called Solar, shown in action on the right here. We now have different linear models at different times. And so we learn to embed into a space where at each time, a local linear model can capture the transition very well. So you still get initial random rollouts followed by learning latent representation and latent dynamics, but now not a single linear model, but a sequence of linear models. And then from that, once we've done that, we can start doing a rollout, infer where we are in the space, getting our linear models, find a sequence of controllers, execute that, get new data, and repeat. That's model-based control in action, a model-based reinforcement in action under this particular setting, where we make the latent space very efficient to find optimal policies in. So might not succeed on the first time around, so get the new data, update the representation, infer where we are in terms of linear dynamics models, and find the updated policy and repeat. And this can actually learn in about 20 minutes to stack a Lego block, learning it from pixels as input. Okay, so we looked at state representations of how to go from raw pixel observation to state learning ahead of time with a VAE in the World Models paper. And we looked at how can we learn dynamics model and mapping from pixels to state at the same time and maybe benefit from that. Now, here's another way we can think about this, which is we could think of putting in some prior information. So when we have pixels as inputs, and we know that under the hood there's a state thing, we know that state is just a bunch of real numbers. So what we did here in this paper is we said, okay, we're going to collect data. We're going to learn a latent representation, which is generated by a sequence of Kahn filters. Then we're going to apply a spatial softmax, meaning we're going to look for each of these 16 filters, where each filter is most active through a spatial softmax, and then output the corresponding coordinates. Those coordinates should allow us to reconstruct the original image because they capture the essence. They're the coordinates of the objects in the scene. If you know the coordinates of the objects in the scene, at least that's the hope, you can reconstruct the scene. And then once we have learned that representation, we could learn to control with just a 32-dimensional input rather than needing to take in 240 by 240 input, which is much higher dimensional and much more expensive to do reinforcement against. This is actually capable of learning a pretty wide range of skills here. So here is the data collection. So it's just randomly moving around, collecting data. That data is used to train that spatial autoencoder. And so then we learn, we look actually, we imprint the goal situation, and then we do reinforcement learning in the feature space, the 32-dimensional feature space, and learn in a relatively short amount of time how to push the block to the target location. Here's another idea you can follow on how to go from image observations to state, or something like state. Very kind of interesting method here, and it actually doesn't bother reconstructing. It says, all we need to do is think about physics. What does physics tell us? Well, we're going to want to find an encoding of state, underlying state, coming from the observation. Phi here will be the big neural network that turns image observation into underlying state. Well, what do we know about state? We know that in physics that there will be coordinates and then derivatives of coordinates, which are the velocities of these objects. So there is a state variable corresponding to velocity and other state variable corresponding to position, and the change in position is velocity. That's we know that velocity is derivative of position. Then what else do we know? We know that when the world can be in different states, we're going to need different state values. So by default, if we get random stuff presented to us, we want the embeddings SA and SB of two different situations to be far apart. So that's what this loss is saying. We want embeddings to be far apart. But if all you do is put embeddings far apart, well, then that's not enough to get any structure. So then the next loss here says that for consecutive times, the position state variables should be close. It also says that between time t and t minus 1, the velocity state variables should be close because velocity cannot change quickly. So that's essentially saying acceleration typically is going to be small. On average, acceleration is going to be small. Then conservation of momentum and or energy is captured in here. And then the last part here is saying that we need a representation where the actions are able to influence what the next state is going to be. So we want a correlation between action and state. All right, so they tested this on a couple of environments here where they would just collect data in these environments, pixel input, and then learn a state representation that doesn't do reconstruction, just tries to satisfy those invariants that are expected to be good loss functions based on physics, and learn pretty interesting state representations that way. Here's another example of state learning in action. Going relatively quickly here to just kind of get a lot of different ideas across. We covered the beta VAE in one of the earlier lectures. Beta VAE is a variational autoencoder where we put a coefficient beta in front of the KL loss on the prior. And by making that coefficient beta bigger than 1, effectively what we're doing is we're trying to make the latent variable z maximally independent. So we're trying to find a disentangled representation of the C. And so the thinking here is that, well, if we want to find something that we think of as state from raw pixel values, then probably we need to find something that's really strongly disentangled. And so it's putting that prior into it. And they show that by having this beta VE, you actually get much better transfer. So they train a beta VE and then do Q learning in a network that takes the embeddings from the beta VE and compare that with regular Q learning. And so on the left here, we see what happens in the training environments. In the training environments, regular Q learning and DARLA, which is Q learning with the beta VE representation learning, do about equally well. But when we look at a new task, related task, but looks very different, by doing the representation learning, which is shown at the bottom right, we actually get much better performance. Top left is actually not getting a job done. It's not collecting these yellow targets, whereas bottom right is really good at collecting yellow targets. And what's changed? Well, the walls in the background have changed to pink rather than green, and the ground has changed to blue rather than yellow. So a relatively small change. The original DQN, because it doesn't do representation learning per se, hasn't learned those notions, whereas the beta VE has somehow learned a representation that allows it to transfer zero shot to this new environment much better. Here's another idea of representation learning for state and dynamics. We looked at GANs in, I think, lecture 4 of this class. Now, if you just train a GAN, what happens is that you just train for each frame independently. What we want is we want to learn representations that are consistent over time. And so what we're going to do is we're going to have a discriminator here that looks at 2 consecutive observations and decides whether those 2 consecutive observations are consecutive observations from the real world and what consecutive observations generated by a generator. And so we have a generator here trying to generate fake sequence of observations, trying to fool the discriminator, and at convergence, what that means is that this generator is trying to generate observation sequences that are indistinguishable from real world observation sequences. Once you have that, you can use that generator as a simulator and learn that simulator or plan in that simulator. In this case, we did planning to try to achieve goals. What you'll see on the right here is we actually did this for rope manipulation. So on the left is the initial state of the rope. On the right is an end state of the rope. And what we see is with causal infoGAN, it thinks that these are the interpolated states. So it thinks that this is a sequence of states you have to go through to go from the initial state to the end state. Same for the next one, next one, next one. Compare that with DC GAN, which we covered, which just doesn't look at transitions, just looks at individual frames. We see that the interpolation here doesn't necessarily lead to intermediate states that are that meaningful for a robot to try to follow that sequence of intermediate states in rope configurations to get from start to goal. And so we're able to, by training an InfoGAN, which looks at realism of transitions rather than just realism of individual frames, is able to learn a dynamics model in a latent space that we can use for robot to make plans. Now, one of the first things we covered was the world models, which show that you can learn a latent space and then learn an RNN on top of the latent space for dynamics, and then learn a linear controller on top of that. Of course, that's a very naive thing. It's almost surprising it works, and what's so interesting that it actually does work in a range of environments. But ultimately, it's not likely to be the final answer to keep it that simple. And so here's a paper called Planet, learning latent dynamics models from pixels plus then planning in it. So what's new here is after learning the latent space dynamics model, it's actually, in this case, not deploying a policy, it's using a planner, using look ahead as a function of which sequence of actions do I get the most reward, taking that first action, that sequence of actions, repeat. And it here learns the latent space encoding together with learning the dynamics model. So it's joint learning of encoding and dynamics. Recently, there's been an improver to this called Dreamer from the same authors roughly. And what they show is that you can actually, rather than planning in latent space, you can actually train a actor critic in latent space simulator, and that'll actually do better than the planner. They also show that the dynamics model you learn, it's better in these environments to learn a stochastic dynamics model rather than a deterministic dynamics model. And those are the two big differences between Planet and Dreamer, going from planning to learning actor critic agent and using a stochastic model. Now, so far we talked about latent space models and directly learning to control in the latent space. There is also work that actually goes back to image space. And so here are some example executions by a robot moving objects to target locations. And this is done by the system here learned a video prediction model. So it learned as a function of action the robot takes, what will be the next frame I see? And as a function of the next action will be the next frame I see, and so forth. Once you have an action conditional video prediction model, and if you have a target frame or target property that you want to achieve, you can now use this action conditional video prediction model as your simulator. And this can give really good results actually, and some examples shown here. The slight maybe downside of this is that often planning can take a long time, because to generate an action conditional video prediction can be fairly expensive. You need to generate actually many of them, because you're trying different sequences of actions to see which one might work the best. And then after you find one that might work the best, it might be a sequence of 10 actions. You take the first of those 10 actions and you repeat that whole process. And so these things tend to be not as real time as some of the other things we looked at, but it's very surprising how all this works. You can do full action conditional video prediction and manipulate objects that way. Now, one thing you might wonder is, it's all good and well to do full detailed video prediction, but is it always meaningful? Imagine you drop a bottle of water, glass bottle of water, drops on the floor. How are you going to do video prediction for what happens there? Very, very hard. I mean, you're never going to have access to all the details of the state of the water in that bottle, the little defects that might be in the water bottle materials and so forth that will determine how exactly this thing fractures. The best you're going to be able to do is probably say, like, I think it's going to break into a lot of pieces and pieces of different sizes, and maybe the neck kind of stays together because it doesn't hit the ground. It's the bottom that's hitting the ground and so forth. And you also don't need the details. Like, to make decisions, you just need to know it's going to break. And so what you could do is say, hey, instead of learning a forward dynamics model and say, I need to learn what the future will look like, be able to predict that, you can say, hey, what if I can predict what action I took? For example, seeing this shattered bottle, I say, well, the action taken was dropping the bottle. And so if I can go from, if I can make that prediction, then I can also understand if I want to achieve a certain goal, what action might lead me there and not lead me there. This is called inverse dynamics. And so that's at the core of many other dynamics models that are being learned, rather than forward dynamics, learn an inverse dynamics model, which is effectively like learning a goal-conditioned action strategy. So now, the specific paper here motivates it as follows. It says, we want to learn a forward model in latent space. And we want this latent space to, of course, compactly represent the things that matter. But if all we care about is latent space predictions, then the problem is that maybe we make our latent space always 0. And we predict always 0, we're always good, but we don't have anything interesting. And so they're going to say, well, we want to learn a latent space where we can predict the next latent state, but to avoid it being all zeros or any other way of being degenerate, we're going to require that from the latent state at the next time, ct plus 1, and the latent state at the current time, ct, we should be able to predict the action that was taken at time t. And so we learn two dynamics models at the same time. We're learning an inverse dynamics and a forward dynamics model at the same time in this latent space. This is applied to learn to poke objects. So what you see here on the left is data collection. You can set this up for autonomous data collection. On the right, what you see is the learned control. So it's learned the dynamics model, and now I can look at the current state, can look at the goal state, and it can do a prediction of which action is going to help the most to get close to that goal state, and can repeatedly do that until it finally reaches something very close to the goal state. Okay, now reinforcement learning is about reward, and so far we actually mostly ignored the reward when we learned representations. And so we'll switch that up now. Let's not just learn to predict next state, but also learn to predict future reward. Kind of first recent paper that looked at this in the deep reinforcement learning context was a Predictron paper. So end-to-end learning and planning. And what they said is, well, it's difficult to know what needs to go into the latent state. And so since we don't really know what has to go in the latent state, and we don't necessarily want to reconstruct the full observation because that's just so many things to reconstruct, and we really want to focus on the essence. Well, if what we care about is getting high reward, should we just focus on predicting future rewards? Because for every sequence of actions, we can predict the future reward, well, we should be good to go. Then we can just pick sequence of action that leads to the highest future reward, and we're good to go. Predictron did this for some relatively simple environments shown here, billiards as a function of which action you take, how will the billiards balls end up, and actually did pretty well on that task, and also looked at it for maze navigation. Now, the most recent result, of course, that you might have heard of that builds on top of this very directly is mu0. mu0 is also learning a latent dynamics model that predicts rewards and doesn't worry about reconstruction. And so this one here does it just given one action in the beginning, what's the sequence of latent states that allow me to predict reward in the future, and mu0, same thing, but now action conditional, and was able to solve a very wide range of game situations. Another variation is successor feature. So you might say, instead of predicting reward, which is just one number, what if reward consists of many components? Maybe I care about location of the robot. Maybe I care about energy expended. Maybe I care about other things. These are all features. And so the idea here is then, if I have a set of features that relate to reward, why not learn to predict, well, learn a latent space model that allows me to predict the future sequence of features encountered. We looked at this ourselves in the context of navigation, actually. So when you have a robot that's navigating a world, it does some convolutional processing of its observations, then there'll be some LSTM, because when you're navigating, you currently see something, but you want to also remember things you've seen in the past. You have some memory here. And then from that, should try to predict observations, features of observations you might see in the future. For example, might I have a collision or something like that? Here's this system in action. So so what we have here, let me fast forward this a little bit to the experimental setup. So what we see here is this is inside a simulator actually for now, but also real world experiments coming later. You see the kind of visual inputs this is processing, and it's trying to predict things about speed, heading, collision. Those are features it's trying to predict. It's trying to predict, this many steps in the future, what will my heading be, what will my speed be, what will my collision be based on what I see right now, and based on the actions I will take in the intervening time. Through that, it's able to learn an internal representation of how the world works, but most importantly, how the world works as it relates to features that matter for navigation, versus try to learn everything about the world, which might be a lot to learn relative to what you actually need to learn to be successful at your task. And so based on that, it's able to learn to navigate these environments pretty well. Then let's look at the real robot. So here we have the actual robot that's going to learn to navigate hallways in Corey Hall over at the electrical engineering building at Berkeley. So we see here, it actually, when it's still learning, has a lot of collisions, but it learns to predict that. It learns to predict, say, if I see this, take that sequence of actions, I will have a collision in 5 time steps, or my heading will change in that way, and so forth. And so after training, it's internalized a lot of how the world works. Now I can plan against that representation. Well, I need to act now. Let's go to, this is test time. It's learned now. We can see that it's learned to avoid collisions. And internally what it's doing, it knows to predict as a function of the actions it's taken, whether a collision is likely to happen or not, what heading it might end up with, and then take actions accordingly. And again, the reason I'm showing all these videos here is because, as you see, different approaches are tested in very different environments. And this is by no means a converged research field. And so there's a lot of variation in how things get tested. And by looking at how it's tested can give you a sense of how complex an environment a certain approach might be able to handle. Now, a natural question you might have is, well, this is all great. There's all these different ways of learning representations. But could we come up with a way of optimally representing the world? What would that even mean? What does it mean to have an optimal representation of the world? Well, there's some work that's actually trying to get at this. So here are some fairly theoretical, to be fair, references on trying to understand what it means to have an optimal representation of the world. And one thing you'll often see come back is this word homomorphism. And what it refers to is that essentially you have the real world, you have a simulator, and you want it to be the case that if you go from real world to some latent space simulator, so you have a one-to-one match that's happening, you go from real world to this latent space representation. At that point, you simulate in both worlds, and then after a while, you try to map back and see if it still corresponds. A homomorphism would mean that you still have a correspondence many steps into the future, or any number of steps in the future. And so that would be kind of a bisimulation homomorphism type approach. And the question, of course, becomes what's the minimal latent space that you need to be able to do that? Because the more minimal that latent space is, the less variables you have to deal with as a reinforcement learner or a planner to try to learn, achieve good reward in the environment. Now, one thing that's very well known in traditional controls is something called separation principle. And separation principle in traditional control says the following. And it's not, well, it's for a very specific scenario. It says, if I have a linear dynamical system, and I have noisy observations of the state, so I don't have access to state, I only have noisy observations. And these noisy observations are linear functions of the state. So linear dynamics, observations, linear functions of the state. Then, to do optimal control in this environment where I don't have full access to the state, all I need to do is to find the optimal estimator of state, which will be a Kalman filter, and use that to output my best estimate of the state at every time, combine it with the optimal controller, assuming I have full access to state. So the separation principle says I can separately design an estimator and a controller. Design them separately and then combine, and that's actually optimal. And that's actually very related to things we've been talking about. We want to do representation learning, we want to do control. We want to be the case that if we do the right kind of representation learning, the representation comes out of it and just be used with optimal control, and we get the optimal result out. And so there's some work now trying to look at what if you have a nonlinear system. You might apply deep neural networks to that system and so forth. What does it mean to have, optimal estimation of state from your observations, and how, when is that compatible with your control and so forth. So very interesting theoretical direction if you're more theory inclined. So another way to think of it is to say, well, shouldn't I just think about it end to end? So often in deep learning, you have kind of two paths. One path is you're going to try to design something, and the other path is you say, hey, let me just think about the result I want. This is the result I want. Let me define a loss function on the result I want, and then train against that, instead of putting all the modules in more detail together myself, let's say. So in this case, what it might mean is, well, instead of learning a representation for a dynamics model and then bolting on a planner or bolting on a reinforcement learning agent, why not say, hey, when I learn my dynamics model, I should train it end to end such that what I learn is maximally compatible with a planner that I will use in the future. So this goes a little bit back to the early thing we covered, the embed the control. We said, if we can learn a linear dynamics model in latent space, planning becomes easy. Here we're going to say, what if we have a more general planner? It might not. And so that general planner might work well in a wide range of situations. Now, can we learn a representation that if we combine it with that more general planner, together they function well? If so, then we learn a good representation. So the way we did this in some early work, value iteration networks led by then postdoc Aviv Tamar, now professor at Technion, we showed that actually value iteration, a very common way of doing planning for tabular Markov decision processes, actually this value iteration process can be turned into a neural network representation. And so we can then bolt this value iteration network onto a representation learning network and optimize them together to try to get good performance out, turning image input into a representation on which value iteration runs, and the encoding of image input will need to be such that the value iteration process actually gets good results. And we even gave the value iteration process some flexibility to learn parts of that. We showed that this way you can actually get very good performance on planning tasks. You might say, well, planning with visual input shouldn't you just be able to learn a ConvNet that just kind of looks at it and makes the right decision? Well, it turns out really, and sometimes what we're doing here is building a very strong prior into that ConvNet by building in the value iteration aspect into it. It's a bit like, why do we use a ConvNet? Well, we use a ConvNet to encode translation invariance, and hence we can learn more efficiently than if we were to use a fully connected network. It's kind of the same idea here. If we learn a network that should solve a control problem that under the hood uses planning, well, then we should just put that planning in the network, the planning structure into the network, so we can learn it all end to end. And now, one question that has often come up in this context is, well, should we ever do pixel level video prediction? Well, that's a good question. I mean, often you're just looking at noise, and what's the point in trying to predict that? What really matters is predicting the things that affect your actions. So how do we do that more directly? So we're going to use planability as a criterion for representation learning now. So value iteration networks, as I've just described, go into a little more detail. It says I have an observation. Observation goes into a module that outputs a value function, which is how good a certain state is. It puts that out for every state that you could have in parallel. Then an attention mechanism will look at the current observation and understand which of all these possible states it should index into, then make a decision on what to do in the current state. The value iteration module looks at essentially value iteration. If you're not familiar with it, essentially what it does is it needs to look at reward and dynamics model, and then based on reward and dynamics model, it can do a recurrent calculation to get out the value of each state. So this is just a recurrent calculation, repeatedly applying the same operation. So it's a recurrent neural network. And it's a recurrent neural network with local calculation, because states next to each other can be visited from each other and happen to show up in this dynamic programming calculation. So it turns out that a recurrent ConvNet is enough to represent value iteration calculation. But we don't need to do it with something like value iteration, which only applies to situations where we can have a tabular representation of the world, which means for very relatively small discrete state spaces. We can do this more generally. So what we're looking at here is universal planning networks. Universal planning network says, okay, we have an observation. We want to achieve a goal observation. We take our initial observation, we turn it into a latent state with an encoder. Then we take an action, new latent state. Oops. We take an action, new latent state. Take another action, new latent state, and so forth. Take another action, new latent state. And after that sequence of actions, we want our latent state here to match up with the latent state of the goal observation that we want to achieve. So what we can do is we can search over actions that will get us close. And so if we had already trained this latent space dynamics model, all we would need to do is to optimize this sequence of actions. And if this is a continuous space, we can optimize a sequence of actions with backpropagation. So we can run standard backpropagation to find a sequence of actions that optimizes how close we get to the goal. So that's the planning part. Assuming we have this dynamics model, we can run backpropagation to plan. How do we get the dynamics model? Well, here's what we're going to do. We're going to learn the dynamics model such that, so we're going to try to find parameters in this dynamics model such that if we use those parameters to run this optimization to find actions, then the sequence of actions we find corresponds to what was shown in a demonstration that we're given. So we're given a demonstration, a sequence of actions, and we'll have an imitation loss in that. We'll say we want to be able to imitate the sequence of actions by running this very specific process of optimizing with backpropagation our sequence of actions against a dynamics model that we're going to learn. Once we have learned the dynamics model this way, what it means is then onwards, we can use this latent space dynamics model to find sequence of actions to optimize how close we get to some other goal in the future. So benefit here is better generalization, better inductive bias than just learning some black box for imitation. And actually also learns a metric in this abstract space that's useful for reinforcement learning in the future. So we compare this with a reactive imitation learner, which just says, okay, I need to just imitate a sequence of actions. But this black box neural net doesn't know that when you imitate, probably the demonstrator had a goal and you're trying to find a sequence of actions that achieves that goal. So it doesn't have that inductive bias, so it's not going to do as well. And something closer to the architecture we use is something that's also a recurrent neural network, but doesn't have the internal optimization process in the inner loop to find a sequence of actions that optimizes how close we get to a goal. So tasks we looked at here was some maze navigation tasks and also reaching between obstacles to a target. The curves you see here on the horizontal axis is the number of demonstrations. The vertical axis is the average test success rate. What we see is universal planning networks outperforms the baselines that I just described. What that means is that building that inductive bias helps significantly in learning to solve these problems. Now, another thing you can say is, well, what did it actually learn? We said we build an inductive bias. We said we build an inductive bias to learn to plan in that inner loop, but is it really learning to plan? Here's an experiment you can do. You can say, what if we learn with 40 iterations of gradient descent to find a sequence of actions? And then we test with a varying number of planning steps, meaning we vary the number of gradient descent steps in the inner loop when we do planning. If our thing is doing planning, then the hope is that by running more planning iterations, it would keep refining the plan and end up with a better plan than if it only has access to 40 iterations. And so that's indeed what we see here. As in the horizontal axis, we increase the number of planning steps, the test success rate goes up for the same amount, same training, just different number of planning steps at test time. So this indicates that likely something like planning is really happening under the hood, and if you plan longer, you can do better. Another thing that happens is when you do this, you learn a representation that ties into how an agent should make decisions. That representation can be used by a reinforcement learning agent to learn more quickly. What makes reinforcement learning typically hard is that the reward is sparse. But if you map your world into this latent space, in that latent space where you're running this optimize, a gradient descent to find good actions, well, gradient descent assumes that there's some smoothness. So once you've learned that latent space where there's smoothness you can optimize against, that probably means that in that latent space, distances are more meaningful. And if you now do reinforcement learning against distances in that latent space, you're doing it against a reward that's better shaped, that's not sparse, but is dense and is giving you a signal locally on whether you're improving or not improving on what you're doing. And so we showed in a wide range of environments that indeed reinforcement learning can be a lot more effective when using the distance in latent space learned in the process I just described, but then you do reinforcement in a new environment. For example, we did imitation learning in 3-link and 4-link environments. Switched to a 5-link environment, ran reinforcement in the 5-link environment space, and the latent space there is used for reward shaping, and I can actually learn a lot more quickly. Same thing here, where the initial learning happened with a point mass and a 2-stub point mass, and then actually had to control an ant robot. And thanks to the shaping that comes from learning this latent representation where distances are meaningful, learning can be a lot more efficient. Okay, so at this point we covered quite a few different ways of combining representation learning with reinforcement learning to be more efficient. And the general theme so far has been that, or at least in under state representation, has been that raw pixels, sure, it has the information, but it's embedded in a very high dimensional space. It's million megapixel image, million dimensional input. We want it in a more compact representation we can learn against more efficiently. And all of these describe observation to state, observation to state, and state action to next state, and so forth, all try to get a handle of that problem. Now, another thing you might observe is that what we covered so far is fairly complex. There's a wide range of ideas at play. And so the question we asked ourselves recently is it possible with a relatively simple idea to maybe get a lot of the leverage that we have seen here? And let's take a look at that and see how far we can get with a relatively simple idea. And actually we'll see outperform essentially all the approaches we've covered so far. That doesn't mean the ideas and the approaches we covered so far are not important. If they were not important, I would probably just have skipped them. There's a lot of good ideas we've covered that we probably want to bring into this next approach we're about to cover. But when I'm about to cover curl, we'll really focus on simplicity and see how far we can get with something very simple. Our starting observation here was, if you look at the learning curves, the vertical axis here is reward and higher is better. Horizontal axis, number of trials in this environment. And so we see like at the end here, 1E8, so 100 million steps have been taken in this environment. And so we see a blue learning curve here that learns very quickly, and then green learning curves that take a long time to learn. What's different? Blue learns from state, green learns from pixels. Same thing here. Blue learns from state very fast, green from pixels not nearly so fast. And this is, in this case, the RL algorithm is a D4PG, which is a state-of-the-art RL algorithm. But if you think about the essence here, reinforcement learning is about learning to achieve goals. And if the underlying space is low dimensional, there is a low dimensional state, shouldn't we be able to recover that low dimensional state and then learn just as efficiently from pixels as from state? And how might we do that? Well, we've seen a lot of success in past lectures with contrastive learning for computer vision. In fact, we saw with CPC that it was possible by using unlabeled data, this is on ImageNet, to consistently outperform learning with labeled data. So unlabeled plus, so it is the same amount of labeled data, but the blue curve also has unlabeled data. We see that the unlabeled data consistently helps outperform having only access to that amount of labeled data. And of course, very recently, SimClear came out as actually getting equally good performance as supervised learning on ImageNet when using a linear classifier, just a linear classifier on top of a self-supervised representation. So that means that almost all the learning happened in self-supervision, and then a little bit of learning happened at the end, of course, to get the meaning of the labels, but it just needed a linear classifier. If that's the case, then the hope is that we do something similar in reinforcement learning. All we need to do is do something where we do representation learning that extracts the essence, and at the end, a little bit of extra information, the reward to do the rest of the learning. So what did SimClear do? It essentially said, I have an image, I'm going to turn into two versions of that same image, and when I then embed them with a neural network, the same neural network in the left and the right upward channels, then the embedding should be close. It was measured with some cosine similarity. And of course, if another image that I embed, then that embedding should be far away. And those are the negatives in the denominator. So if you want more details on that, of course, go back to our self-supervised learning lecture from a few weeks ago. What's important here is that this is a very simple idea. It's just saying, turn an image into two images, and the embedding should be close. Take a different image, its embedding should be far from this. What's surprising about this, even though it's relatively simple, it enables representation learning that then on top of that, all you need is a linear classifier to get really good ImageNet classification performance. And they actually looked at many types of augmentations: cropping, cutout, color, Sobel filter, noise, blur, rotate. And what they found is that crop matters the most, and color matters quite a bit too, but really cropping is the one that matters the most. So now to curl. Curl looks at contrastive representation learning with RL. So what do we do here? We have our replay buffer, on which we normally would just run reinforcement learning. And so we have our replay buffer. We take an observation out of the replay buffer. Since this is a dynamical system, we need to look at a sequence of frame and consider that a single observation. Otherwise, we cannot observe velocity. In a single frame, we cannot observe velocity. So we'll have a stack of sequential frames that we together consider a single observation. That stack of frames then undergoes data augmentation, two data augmentations, in this case, two different crops. Then one goes into the query encoder and one goes to the key encoder. This could actually be the same or it could be different, you can choose. And then ultimately, you do two things with this. In the top path, it just goes to the reinforcement learning loss. So if you run D4PG again, or you run soft active critic, you run PPO and so forth, that happens along the top path. So what it means is that along the top path, you run your standard RL algorithm. The only thing that's changed is that when you take things from your replay buffer, you do some data augmentation on it. In the bottom path, you have another data augmentation of the same frame. You have a contrastive loss. So essentially, same loss, not exactly the same details, but at a high level, same as what we saw on the SimClear slide. Okay, so a couple of things that were important to make this work. SimClear uses a cosine laws. What we found is that having a weighting matrix here between the key and the query is actually important. And we see in the red curve, the bilinear and weighting is significantly outperforming using just cosine. The other thing we notice is that using momentum in one of the encoder paths is very important too, which was actually done, as we saw in the self-supervised learning lecture, in the MoCo work. They also have momentum in one of their paths. Same thing was important here. Again, big difference. So once we do that, we can see that curl outperforms both prior model-based and model-free state-of-the-art methods. So what we look at here is median scores. On deep mind control 100K and deep mind control 500K. So it's 100K steps or 500K steps. And so it's checking really, can you learn fast? It's not about after 100 million steps where are you at. It's about 100,000, 500,000 steps, where are you at? And so we see here, after 100K steps, from state, if you have access to state, this is how far you get. Curl on 100K steps is a little bit behind on what you can do from state. But on 500K steps, it's actually all the way there. So we see that we can learn almost as well from pixels as from state with curl. If we look at prior methods that also try to learn from pixels, we see that they consistently are not doing nearly as well after 500K steps, and same with after 100K steps. So both after 100K and 500K steps, curl outperforms all prior RL from pixels on Deep Mind Control Suite, and it's actually getting very close to state-based learning. Here we have the learning curves. In gray, we see state-based learning. In red, we see curl. We see that in many of these, red is matching gray. There are a few exceptions, but in most of them, red matches gray, meaning that with curl, RL from pixels can be almost as efficient as RL from state, at least for these deep mind control tasks. And here we'll look at a table of results. We see in boldface the winner compared with all prior methods, state-of-the-art methods of learning from pixels, and we see that consistently curl outperforms the other methods for the 500K and 100K, not just on average, but on essentially all of the individual tasks, except for the one here and one here. There are a couple of environments where curl doesn't learn as fast, and we'll look at the details. What happens there? These are environments where the dynamics is fairly complex. So this requires some more research, but our hypothesis here has been that in those environments, learning from pixels is particularly difficult because if you just look at the pixels, the dynamics is not well captured in the sequence of frames you get to see. For example, if contact forces matter a lot, then you can't easily read those off from pixels. And so having access to state makes a pretty big difference in terms of being able to learn. Looking at the Atari benchmark, we are looking at median human normalized score across 26 Atari games at 100K frames. And we see that compared to prior state-of-the-art, Rainbow DQN, simple and, well, efficient Rainbow DQN, simple and Rainbow DQN, curl significantly outperforms prior state-of-the-art. And it's getting at about 25% of human normalized score. Here's it broken out for the individual games, and curl is outperforming prior state-of-the-art fairly consistently, with simple coming in first on still 2 of them. So can pixel-based RL match human data efficiency? It's a good question. Human normalized algorithm score, we see on Freeway and on James Bond that we get pretty much the level of human efficiency. For the other games, there's still a bit of a way to go, but it is not, I would say it's night and day. It's, it's already double-digit percentage performance relative to human on almost all of them. Okay, so we looked at 2 main directions in representation learning and reinforcement learning so far, using auxiliary losses and doing things that effectively come down to trying to recover underlying state with a self-supervised type loss. Now, there are other ways representation learning can help, namely in exploration, which is one of the big challenges in reinforcement learning, and in unsupervised skill discovery. So let's look at those 2 now. First way it can help in exploration is through exploration bonuses. So what's the idea here? In a tabular scenario, meaning a very small reinforcement learning problem where the number of states you can visit, you can count them. Let's say there's only a grid world. The agent can be in only 1 of 16 squares. That's it, only 16 possible states. A very simple thing to do is you give a bonus to the agent for visiting grid squares it hasn't been to before or hasn't been frequently before. That encourages going and checking things out that you don't have much experience with yet. That can be very effective in these small environments, but it's impractical for large continuous state spaces because in a large, let's say infinite state space, infinitely many states, well, there's always more stuff you haven't seen. So you need a different way of measuring what makes something new versus something already maybe understood. So one big breakthrough in this space was to look at using generative model, in this case, a pixel CNN for density estimation. So the idea here is you play in a target game, or the agent's playing a target game, and you want to measure how often has the agent been in this state. But if you measure specific states, there's too many of them. So instead what you're going to do is you're going to train a pixel CNN model on what you see on the screen. And things you've seen so far, the more often you've seen something, the higher the log likelihood under that pixel CNN model. But when you, let's say, enter a new room in this game, first time you enter the new room, the log likelihood of that new thing you see on the screen will be very, very low. Will be a bad score. That is a signal that this is something you need to explore because you're unfamiliar with it as measured by the low log likelihood score. And so you can effectively give exploration bonuses now based on the log likelihood scores under your pixel CNN model that you train online as your agent is acting in the world. There's a comparison here between using that versus just using random exploration, and it helps a lot. Another way to do this, you can train a variational autoencoder, which leads to an embedding. And then you can map these embeddings into a hash table and just do counting in that hash table. And that's something we did a couple of years ago, and indeed helps a lot in terms of giving out the right kind of exploration incentives to explore difficult to explore environments more efficiently. Another thing you can do that kind of gets maybe more at the core of what you really want, but is a little more complicated to set up, is variational information maximizing exploration. So the idea here is the following. When you are in a new situation, what makes it new? What makes it interesting about it being new? Well, one way to measure this is to say, hey, if I'm in a situation where after I take an action, I cannot predict what's happening next very well, then I'm unfamiliar with this. So I should give a bonus for having gone into unfamiliar territory. That's called curiosity. We'll cover that in a moment. That's actually been pretty successful, but actually it's also a little defective, because if you just have something that's stochastic in the world, let's say you roll some dice, well, it's going to be unpredictable. So to make this more generally applicable, one thing you can do is you can say, hey, I don't want to be getting exploration bonuses when something is inherently unpredictable. I only want to get them when it's something that's unpredictable because I have not learned enough yet about this. And so the way we did this in Vime is say, okay, you can set up a dynamics model that you're learning. And as you learn the dynamics model, as new data comes in, you can see, you actually set up a posterior over dynamics model. So you have a distribution over possible dynamics models. As new data comes in, you update that posterior. If that updated posterior is very different from a previous posterior, it means that you got interesting information. It allows you to learn something about how the world works. So that should give you an exploration bonus because you did something interesting to learn about the world. But with rolling the dice, if you've seen dice rolled many, many times, and then it rolls again and you couldn't predict it because that's just the way it is, you cannot predict. But your model for the dice will already say it's uniform, over all possible outcomes. That model will not see much update, if any, and you'll not be given an exploration bonus. And so that's the idea in Vime. Only get exploration bonuses when it updates your posterior over how the world works. And again, shown here that helps a lot in terms of exploring more efficiently. Under the hood, that's really self-supervised learning type ideas for dynamics models, ensembles, or Bayesian representations of dynamics models, and then given exploration bonuses based on that. The simpler version of that is called curiosity, where you more directly look at, was something predictable or not predictable, and more deterministic environments, often that's actually enough, and that's seen a lot of success in many of these game environments. Another thing you could do with self-supervised learning or representation learning for exploration is to think about it in a more deliberate way. You could say, hey, it's not just about getting bonuses after experiencing something new. It should also be about thinking about what I should even do before I experience it. Can I set a goal for myself that makes for a good goal when I'm trying to explore? So in GoalGAN, what's done is the idea is the following. You have in this case, let's look at iteration 5 down here. You have a set of points that you reached in this maze. You start at the bottom left, you did a bunch of runs, you reached a set of points. And what you notice is that when you set the goals, in the green area, you're able to consistently achieve your goals. When you set them in the blue area, it's high variance. When you set them in the red area, you usually don't achieve your goals. What you can then do is you can say, oh, I should in the future set my goals in the blue/red area because that's the frontier of what I know how to do. And so how you're going to do that, you're going to learn some kind of generative model to generate goals in that regime. In GoalGAN, the generative adversarial network is trained to then generate goals at the frontier of what you're capable of. And this allows you to explore environments much more efficiently because now you're setting goals to go to places at the frontier of your capabilities and you're continually expanding your skills. You can also do this with a variational autoencoder. That's done in RIG, where the variational autoencoder is generating new goals. Those goals are not necessarily at the frontier in the same way. They're essentially goals that are similar to things you've seen in the past, but the hope is that frequently enough you're at the frontier that you learn relatively quickly. You can also reweigh those goals based on how much they're at the frontier, measured in something called SKUFit, which is an extension to this paper that in some sense changes the sampling in latent space to get closer to sampling from the frontier rather than just from what you've seen in the past. And so RIG itself, here are some examples of this in action. You see robots learning to reach and to push. So that's the kind of thing that is pretty hard to explore for because normally a robot would just be waving in the air and so forth. But here you can set goals that relate to moving objects around, and then it would be inclined to move towards object and push them. Now, another thing you can do in terms of exploration and leveraging generative models or unsupervised models is skill transfer. And this should remind you of how we initially motivated unsupervised learning, or some of the motivation, which was transfer learning can be very effective with deep neural nets. Now, wouldn't it be nice if we can do transfer learning from a task that does not require labels into a task that requires labels? That's transfer from an unsupervised learning task to then fine-tune on a supervised task. Well, similar ideas can be at play in reinforcement learning. So what's going on here? So far, we mostly talked about going from observations to state, those kind of representation learning. But there's another type of representation learning that matters. Representation learning around trajectories, behaviors, tasks. The question here is, how do we supervise representation learning for these things? What's the contrast? What's done now? To explore, you maybe put some noise in your action, and that way you have some random behavior and you might explore something interesting. It's going to take a long time. Sometimes it's shown to be a bit more effective when you explore by putting randomness on the weights in your neural network. That way you kind of consistently deviate in one way or the other. So the good example of where the thing on the right works better than the thing on the left is, let's say you're supposed to explore a hallway. The one on the left would random walk left, right, and would take very long to get to the end of the hallway and explore both ends of the hallway. The one on the right would induce a bias to walk to the right, and maybe with another random perturbation, induce a bias to go to the left, and maybe after a couple of rollouts would have gone to both ends, and that's it. But it's still really counting on luck. It's not really using any knowledge about experience from the past to explore something new more quickly. And that's really the question we're after. Can we use experience from the past to now learn to do something more quickly? For example, if you have been in an environment shown on the left here where when you're in the environment and you don't get to see the red dots are just for us, but imagine you cannot see as a robot the red dots. And anytime you get dropped in the environment, the reward is at a spot on that semicircle, but you don't know which spot. And so you have to go find that reward. After a while, you should realize that I should go to the semicircle and see which spot on the semicircle has the reward. And that will be a more efficient exploration than to just randomly walk around in this 2D world and then randomly maybe run into the reward on that semicircle. Or shown on the right, imagine you're supposed to push a block onto the red flat target in the back, but you don't know which block you're supposed to push. Well, you'd have a very good strategy saying, I'm going to push the purple one. No reward. Okay, I'm gonna try to push the green one. No reward. Try to push the cyan one. No reward. Push the yellow one. Reward. Then I push the yellow one again and keep collecting reward. That's what we would do as humans. But how do we get that kind of exploration behavior that's much more targeted than random motions into an agent? How to get to learn to do that? Well, what we really want then is somehow a representation of behaviors. For example, pushing objects makes for interesting behavior that often relates to reward, whereas random motion where the gripper does not interact with objects will rarely be interesting and rarely lead to rewards. That's the kind of thing we want to learn in our representation of behaviors. Here's one way we can do that. This is a supervised approach, but just to set some context, so not unsupervised, supervised for now, but then we'll go from supervised and transfer to unsupervised and transfer very soon. Imagine you have many, many tasks. For each task, you have a discrete index into the task, which you turn into an embedding. That embedding is fed into the policy, the current state or observation fed into the policy, and the policy take action. If you train this policy for many, many tasks at the same time, then it'll learn, depending on what task you're presented with this index D, to take a good action for that task. But now the additional thing done here is that this latent code Z here is forced to come from a normal distribution. What does that do? That normal distribution means that even in the future, we don't know what the task is. Nobody tells us what the task is. There might be a new task. We can actually sample from this distribution to get exploratory behaviors. We can say, oh, let's sample this Z, let's sample that Z, and the policy will still do something very directed, something that relates to maybe interacting with objects, as opposed to just some random jittering. To make this even stronger the case, there's a mutual information objective between the trajectory and the latent variable Z here. So it turns out this actually helps. So you learn on a bunch of tasks this way, and you have a new task, and you explore by generating latent code Z, and then at some point you'll find a latent code that actually leads to good behavior, and you'll start collecting higher reward. Can we make this a little less supervised? Can we do this a little differently? Another way you can do this is say, well, let's not even have discrete task indexing. Let's just have a latent code going in and learn a policy that pays attention to the latent code while collecting reward. Why would that happen? Well, there will still be many tasks under the hood, but we're not telling it to index into the task. We're just letting it experience reward. And so what it'll learn to do is it'll learn to sample a Z, see whether that Z leads to successful behavior. If it does, then it'll reinforce that Z. If it doesn't, it'll have to sample a different Z and so forth. So here's some task families. Every dot on the semicircle corresponds to a different task. So the hope here is that it would learn to associate different Z's with different spots in the semicircle, such that when it later explores by sampling different Z's, it would go to different spots in the semicircle, and then the one that's successful be able to reinforce that. Same for the wheeled robot here, and here's the block pushing task. Looking at the learning curves, we see that indeed, by essentially getting to pre-train on this notion of indexing into tasks or a distribution over tasks, and then be able to explore by sampling possible tasks, it's able to then, in blue here, learn very quickly to solve new tasks compared to other approaches. The generated behaviors we see are also very exploratory. We see that the exploratory behaviors indeed correspond to visiting the semicircle. In this case, the wheeled robot, and in the middle here, it's the walking robot, and on the right is the block pushing. What would this look like in a naive approach? If you didn't do representation learning for exploration behaviors, you would, instead of having these nice push behaviors, you'd have just some jittery behavior of the robot gripper that wouldn't really interact with the blocks or get any block to the target area. After it's done those exploratory behaviors, of course, the next thing will happen is a policy gradient update that will update the policy to essentially sample Z from a more focused distribution that focuses on the part of essentially what corresponds to the part of the semicircle where the target is, or the block that needs to be pushed. Okay, now what we did here was transfer from having a set of tasks to now solving a new task relatively quickly by having good exploration behavior. But we still needed to define a set of tasks and then transfer from that. So the question now is, can we do completely unsupervised skills? Can we just have the robot learn on its own to learn a range of behaviors, and in our test time, explore in a meaningful way to zone in on a specific skill quickly? Let's take a look. So it's actually multiple lines of work that effectively do the same thing, but slightly different objectives, but the same high-level idea. So the high-level idea is we're still going to have a policy pi that conditions its actions on the observation, the current state here, and a latent code, which might or might not come from a discrete code, but only has to come from a latent code that comes from a normal distribution, so we can resample this in the future. This will result in trajectories. And so the way we're going to pre-train this is by saying that there needs to be high mutual information between the trajectory that results from this policy and the latent code it's acting based upon. So you start your rollout. At the beginning of your rollout, you sample Z. You keep Z fixed for the entire rollout. You get a trajectory. And you want that trajectory to say something about whatever Z was that you used for this trajectory. What does it mean to have high mutual information between trajectory tau and Z? Well, I can measure it in many ways, and that's what these 4 different papers are. The first paper looks at actually the discrete variable in a trajectory. And the second paper looks at Z and the final state. The third paper looks at Z and every intermediate state independently summed together. And then the fourth one looks at Z and the full trajectory as a whole. And they all give fairly similar results, actually. So here's the third paper, Eisenbach et al. Paper, showing a range of behaviors that comes out of this when you apply this to the cheetah robot. So for different Z's, you get different behaviors here, meaning, and we see high mutual information indeed. We use different Z's, and the trajectories look very different to us, meaning that indeed a different Z results in a very different trajectory. And of course, the beauty is once it's learned to generate all these behaviors for different Z's, now at test time, you need to do something else. Let's say you need to run at a certain speed. There will be Z's that already correspond to running forward, and then you can fine tune the Z directly rather than need to learn a policy. You just need to figure out the Z that will result in the behavior that you want. Here are some videos from the paper, the Abbeel et al. Paper, looking at and generating all kinds of different trajectories corresponding to all kinds of different latent variables Z. So we see for the same latent variable Z, the same kind of trajectory gets output. And here's some more videos. Oh, some of these cannot be played for some reason. But here's a cheetah robot with the Abbeel et al. Approach. And so this is kind of just not to show that, you know, Abbeel et al. Might be better than the Eisenbach et al. I think it's just to show that actually it's very similar. So the difference in those 4 objectives might not be too important, actually. Some limitations in this approach, this also comes from the Abbeel et al. Paper, is that when you have a humanoid, which is very high dimensional, compared to cheetah, which essentially just kind of stands up or runs on its head, humanoid is high dimensional. You try to find high dimensional information behaviors between Z and trajectories. It can take a long time, or it can have a lot of mutual information with all trajectories actually being on the ground, because there's a lot of different things you can do on the ground, and it's not something where you necessarily automatically get it to run around, because running is very hard to learn, whereas doing all kinds of different tricks on the ground is much, much easier. Okay, so let me summarize what we covered today. We covered a lot of ground, much more quickly than in most of our other lectures, because this lecture here is more of a sampling of ideas of how representation learning and reinforcement learning have come together in various ways than, you know, a very deep dive in any one of them, as we've done in previous lectures. The big high-level ideas are that when you train a neural network in deep reinforcement learning, you might as well give it auxiliary losses. And if those auxiliary losses are related to your task, well, they might help you to learn more quickly than if you did not have those auxiliary losses. And of course, the most canonical paper there was the Unreal paper. Under the hood, a lot of this ties to state representation. If we have high dimensional image inputs, Well, ultimately under the hood, in these tasks, often there is a low dimensional state. And so there's many things you can do to try to extract a latent representation that is closer to state than the original pixels. Once you're working with that latent representation closer to state, or maybe even matched with state, learning might go a lot more quickly. And in fact, we've seen that with the curl approach, it's possible to learn almost as quickly from pixels as from state. It's not just about turning a raw sensor observation into a state. There's other things you can do with representation learning in RL. You can have it help with exploration. You can have it help in exploration by helping you generate exploration bonuses, essentially measure things that are new. Canonically, in tabular environments, you measure by visitation rates, but in high dimensional spaces, you'll always visit new states. So you need to measure how different that new state is from past states, which you can do with generative models and likelihoods. Another thing you can do in terms of exploration is you can think about generative models for behaviors that are interesting, such that now exploration becomes a matter of behavior generation rather than random action over time. Or you can learn generative models for goals that might be interesting to set, and then set goals with your generative model for your reinforcement agent to try to achieve, to expand its frontiers of capabilities. And another thing you can do is unsupervised skill discovery. In unsupervised skill discovery, what we do is we essentially have no reward at all in a pre-training phase, but the hope is that the agent nevertheless starts exhibiting interesting behaviors that are reusable, that lead to reusable skills for future learning against rewards that we actually care about. So that's it for today's lecture in terms of what we're covering. There are a couple of different threads that we didn't cover that I still want to put in references for here on this slide. So I also recommend checking those out if you want to learn even more about representation learning and reinforcement learning. All right, thank you.